Hello everyone. Today in operations research subject we will be talking about nonlinear programming problems. In short, we write as NLPP. So nonlinear programming problems, already you have idea about linear programming problems. So let us see a little bit about linear programming problems, and then we will go for nonlinear programming problems. So what is linear programming problem? So in linear programming problems, all the functions will be linear. What is the meaning of linear? So linear functions means the exponent of each term in the function will be either 0 or 1. Okay, so that is known as linear function. And so we know that why it is called as linear also, that because the graph of the linear function will always be a straight line. So let's see one example. We can see the example of a linear programming problem. Like I told that all the functions of the linear programming problem will be a linear function. So let us see an example of a linear programming problem. So generally in linear programming problem, we have two types of functions. One is known as objective functions, and another one is constraint function. So let's see the objective function. So maxima is z is equal to 3x1 plus 5x2. So this is known as objective function. This objective function has certain constraints. Okay, so we will write the constraints as subjected to x1 less than equal to 4, 2x2 less than equal to 12, 3x1 plus 2x2 less than 18, and x1 greater than 0, x2 greater than 0. So this is a example of linear programming problem. Here we can have all the functions. Here is the constraint functions. These are basically the constraint functions. Constraint means basically it is restriction. Means these are the restrictions which is put over this objective. The objective is to maximize this function, but we cannot maximize unlimitedly. Rather we need to follow certain restrictions. So this is one linear programming problem. So next we will see that what is nonlinear. So any function which is not linear will be called as nonlinear functions. And actually in practical problems, nonlinearity is not an exception. It doesn't actually happen that when you are solving any practical problem which you will be seeing in the industries. So it's not that they will be always linear functions. There will be you will find sometimes nonlinear functions also. So this is not an exception. That means you cannot avoid nonlinear functions. You have to deal with the nonlinear functions. So that's why this subject or this topic has been put here, is about the nonlinear programming problems. So what basically is nonlinear programming problem? So if the objective function you find is nonlinear, then that problem will be known as nonlinear programming problem. Or if objective function is linear, but constraints are nonlinear, in that case also it will be known as nonlinear programming problem. If the situation is like that the objective function and the constraint function both are nonlinear, so that is also known as nonlinear programming problem. So let us see one example. um, let's see that which kind of functions are known as nonlinear programming problem. So here is an example. Maximize z is equal to 3x1 plus 5x2 subjected to x1 less than 4, 9x1 square plus 5x2 square is less than 216, and x1 greater than 0, x2 greater than 0. So now you can see in this problem that the objective function is same as the previous example which I have given. Even the first constraint is also same, but there is a constraint which is coming which is not a linear function. So this one is not a linear function. So it's a non-linear function. Okay, so now because any of the constraint, because any of the function in the programming problem, if it is non-linear, then the whole problem will be considered as non-linear programming problem. So let's proceed further and see that what are the different topics which we will be discussing in this chapter. So here is the nonlinear programming problem. These are the not visible. Okay, so here we have all the topics. First topic which we will discuss is graphical illustration of a nonlinear programming problem. Then we will talk about unconstrained optimization. I told you that there will be always constraints, so it may not have any constraint also, so that problem is called as unconstrained problem. Okay, so that is to be optimized. So that kind of problem we will see unconstrained optimization. There are two methods for that. Then constrained optimization with one method. So these are the two topics we have to just discuss in the non-linear programming problem. After that we will go for integer linear programming problems and then dynamic programming problems. So we need to only discuss about the three cases. So let's go for the first one, that is graphical illustration of a nonlinear programming problem. So graphically, is it possible to solve the nonlinear programming problem? We have seen linear programming problems solved with the help of graphs when the variables are only two. But what about nonlinear programming problem? So let's see that what are the similarities or differences between the solution which we get while solving linear programming problem and nonlinear programming problems. So obviously, yes, it is possible to solve nonlinear programming problems graphically when the variables are only either 1 or 2. If the variables are more than 2, then it is not possible to solve it graphically. Okay, so actually just see the problems which we have. So we will compare the graphical solution of both the type of problems like LPP and NLPP. So let's see an example of LPP. So we have already given that one example, that was maximize z is equal to 3x1 plus 5x2 subjected to the constraints. What are the constraints? X1 less than 4, 2x2 less than 12, 3x1 plus 2x2 less than 18, and x1 greater than 0, x2 greater than 0. And another problem which we have seen, that is the objective function was same, maximize z is equal to 3x1 plus 5x2 subjected to first constraint is same, the second constraint has some issue, 9x1 square plus 5x2 square, which is linear, actual non-linear function, and x1 x2 greater than 0. So these are the two problems. Okay, so we will see these two problems in the next slide. So let's talk about the graphical solution of linear programming problem. Okay, so we will remove this one first and we will solve the first one here. Okay, so this is the problem which is to be solved. So let's see how this problem is solved. So we know how to solve this linear programming problems. What we do, we plot all the constraints and we find out the feasible region. Okay, so let's draw the diagram. Okay, we will write 1, 2, 3, 4, 5, 6. Actually, up to where we have to go, here is x is equal to 4. So okay, x2 6 means we need to go for 6 here. 1, 2, 3, sorry, 4, 5, 6. Here if we put x1 then it will be 9. X2 is equal to 9. Oh, that means we have to little bit shift it. Okay, wait a minute, just remove all this because it is not possible to draw. So what I'm going to do is, up to 9 we have to go there now. Just take this one. Okay, now this is 1, this is 2, 3, okay, let's see. x1 is equal to 4, means less than equal to 4. That means the line will be at this point. So this is the boundary. Next is x2 is less than 6. This is the boundary. Wait a minute. Okay. Then x1, this line how we will draw? x1, x2 will be 9. So this is point. And x1 will be 6, means this is the point. So just join these points. Sorry. Okay, this is a line. So just name them so that we don't forget or we don't get confused. So this line is 3x1 plus 2x2 is equal to 18. This is x1 is equal to 4 and this is x2 is equal to 6. Now the point is that it is told that x1 should be less than, means this is the region. Okay, x2 less than 6 means this is the region, and less than means this should be below. So obviously this should be surrounded. But the one point is here, x1 greater than means we cannot go this side or this side. So this is the feasible region. So just we will show them. Let's make this highlight, use the highlighter. Okay. So just we are using the highlighter to highlight the feasible region where you will get the solution. Clear? So this is the region. Okay. Now under this feasible region we have to find out the x1 and x2 for which z is maximum. Under this only, we cannot go beyond. Like x2 we cannot take 7. Why? Because x2 is written x less than 6. So x2 maximum we can go is 6. Equal to also written, so maximum we can go is 6. Similarly x1 we cannot go beyond 4. So maximum we can go is 4. So let's see that where it will be lying. So how do we graphically we solve? So we give any arbitrary value to this. Let's suppose we take okay, so we just take it as 5 3 15. Then x1 will be, if x1 is 0 then x2 will be 3, x2 3, this is the point. If x2 is 0 then x1 will be 5, this is 5. So the line which is coming is basically the just draw this one, this point and 5, no? Okay, so this is the line, this is the objective function line. Now this as soon as you take 30, what will happen? X1 will be 6, so here, and x2 will be 10, so somewhere here this is 10. So when you will be joining them, then it will be like something. Now you see these two lines are parallel to each other. Okay, and so objective function, whenever you are putting some value to this, then you are getting parallel lines, and this is objective z is equal to 15 and this is z is equal to 30, means if you want to maximize, then you have to go which side? So you have to go this side, means upper side of the line. Okay, so here you can see this is not the optimum value, z is equal to 30. Why? Because above this also some points are there where you will be getting more than 30 value. So what we have to do, just we have to translate parallelly in this direction. Objective function will be translated parallelly in this direction, so that we will get a point after which there is no feasible region. So when you translate it, it happens that the line passes through this point. Okay, this parallel line passes through this point. This is the corner point which is we are getting is the solution. So this is this point is actually this one is if we put x2 is equal to 6, then we are getting x1 is 2. Okay, so this is 2 and 6. So this is the solution of this. At this point only you are getting the maximum value of z. Okay, how much is that? So the solution has come, that is 2, 6, and we are getting, this is a corner point, isn't it? See, these are the corner points. Generally in the school time when we were solving this type of problems, what we were doing, we were seeing all the corner points which we are getting here. We have 5 corner points, so at every corner points we were checking x1 is equal to 0, x2 is equal to 0, just put it here, you will get z value something, so that is 0. Then here it is 4 0, so just put it there, you will get 12. This is some point, I think just put it 4, then sorry, here put it 4, 12, 6, 3, this is 3, so 4 3 we are getting, so just put it there also. So like that, all the corner points we were checking, and we were checking for which corner point z is maximum, that will be the solution. But that is not the graphical method. Actually graphical method means that you use the graph to find the solution. So when you are translating this curve, then it is passing through this point, and that is the last point in the feasible region, beyond which, as soon as it will cross this point, then this line will not have any point lying in the feasible region. So you have to stop at this point, clear, and you will be getting the maximum value here. So that is how much maximum value, z is equal to, and that is z max is equal to 6 plus 30, 36. This is the maximum value. So this is how you were solving the graphical solution of linear programming problems. So let's go to the non-linear programming problem 1. Okay, so let's see the non-linear programming problem. So that same example we will take, which we have seen in the last example, in the example which we have given one non-linear programming problem, that is maximize, if this is the problem, z is equal to 3x1, same subjected to x1 less than 4, 9x1 square plus 5x2 square less than 2 and 6, x1 greater than 0 and x2 sorry greater than 0. Now solve this problem. So same method we will use, that is to draw the okay, here same thing, x1 4 obviously, so we will be going for 4, 1 2 3 4. Okay, this curve basically where it comes, this is a an arc actually, or you can say circle. No, sorry, not circle, it's an ellipse. So ellipse, we will see that from where it is passing. So let's draw the coordinates 3, 4, 5, 6, 7, 8. This is x2 and this side is x1. Okay. So the curve, okay, first one is this one, so there is no issue in it, we can just draw it. Okay, next is this one, so it will be basically the ellipse, and we find the value of ellipse x1 is equal to 0. If you put, then x2 will come 216 by 5 root under of that, and that is between 6 and 7. So just take a point here. Similarly, if you put x2 is equal to 0, then x1 will come, x1 is equal to 216 by 9 root under. So that will be 30, 24. Root under 24 is around so the curve will be basically like this, something like this. Okay, so this is the feasible region. Are you getting? So this is the feasible region. So just make this feasible region as okay. Now where is the, now all things are over. This is the feasible region. Now just draw the objective function. So let's draw the objective function, that is 3 and 5. Now it was 5, it was 5. So 3 and 5, it was passing through 3 and 5. So just this one, and now you translate this objective function this side, you will find that the objective function is passing through one point here. It will be just like a tangent, and this point will be basically the same point. When you will see, you will solve, then you will get this will be the same point as that in the previous example, that is 2 and 6. So the solution here came same, but you can see here one issue is there, that now in this problem this is not a corner point. Are you getting or not? This is not a corner point. Earlier in the linear programming problem, what we are getting, we were getting the solution at corner point, so we need not to go for the graphical solution, but here we have to go for graphical solution, and we have to find at what point it is tangent. So that point we have to find out. That means that one problem with the nonlinear programming problem is one difficulties, that the solution may not be a corner point. Are you getting? So solution is same. Okay, so the solution is 26 and the Z max value is 36. Okay, so this is one problem. Okay, now see another cases. So this is what, however, it is not a corner feasible solution. Okay, so non-linear programming may have optimal solution which is not a corner point. Okay, so it is not as simple as linear programming problem. Let's see another example. So feasible region is almost same. Now you see in the earlier non-linear programming problem, here was a non-linear function, but now the constraints are all a linear functions. These are all linear functions. Okay, but you see here, this one, this is a nonlinear function, so this will be a nonlinear programming problem. Now the point is that okay, how you will be solving. So feasible region will be similar to the first problem which we have solved, okay, but the objective function will change now. And you see, for different value of x1 and x2, we are getting different z values. And you see that the z value, as z value is increasing, this is shifting in upward in this direction. That means you will be getting the maximum value in this direction. So you have to find the point, that single point through which this objective function is passing, after which the objective function will be out of the feasible region. So that point is this one. Okay, and what is that point? So here we have the solution. Ah, 8/3 and 5. So the solution is 8/3 and 5. So this is the solution. Okay, so still this is lying over the feasible region. Obviously this is not a corner point, obviously. So any different kinds of problems may come. In this problem only the objective function was nonlinear, but all the constraints are linear. Some problem may come where you will find that objective function and constraints are nonlinear, both are nonlinear. So in that problem, say similar situation will be there. Next, one more example we see, and then we'll proceed. Okay, this is one more example, that is z is equal to, objective function is changed now and the constraints are same. So the curve which will be coming, this is actually a ellipse. This is a formula, or you can say equation of ellipse. So feasible region is same. Only thing is objective function has changed, and we are seeing that for the as the z is increasing, the circle, ellipse is becoming a smaller and smaller. Now obviously the value, or you can say the value of z will be maximum at the center, because as the circle is becoming smaller, z value is increasing. So the value of z will be maximum at center, and the center is lying inside the feasible region. Now see, all the previous three problems we have seen that the solution was lying on the boundary, but here the solution is lying inside the boundary. So now nonlinear programming problems may have solution which is inside feasible region. It may not be on the boundary. तो पहला problem तो हमने देखा, we have seen that non-linear programming is not as simple as linear programming problems, because the solution was not on the corner points. Second, we saw that the non-linear programming problem may have a solution which is not on the boundary itself. It will be inside the feasible region. So that is another complication in the nonlinear programming problem. So obviously here the optimal solution is 3, 3, and this is what? That the solution will not be on the boundary.